Hello everyone. Welcome to Mathematics, Physics, Mathematical Physics channel. Today, we're going to talk about another episode of the Math Puzzle series. In this episode, we're gonna solve a rather hard inequality problem together. So, let's do this. If you are new to the channel, make sure to subscribe and turn on the notification bell, so you won't miss future episodes. Keep in mind that the aim of this channel is to represent the beauty of mathematics and physics, and the pure connection between them. So, watch other videos on our channel, and support us with your comments and suggestions. Let's see what we must do. In the given problem, we have to find the interval for x that satisfies the inequality. Please give yourself a few minutes to solve this problem. After a short pause, we're gonna solve it together. If you look closely at this function, it includes a product of a polynomial and an absolute value function and a division by another polynomial. So, if we can determine the sign intervals for each function, then we can determine the sign intervals of the whole function by the product sign rule. For this, better to construct a big table, and analyze all term in the table. You'll later see this table makes our lives much easier. So, on the left side we write each separate term, and on the top side we write the different intervals of x from -infinity to +infinity. We start from the absolute value function. We know that by the definition of the absolute value function, it always gives a non-negative value. It gives 0 if the function inside the absolute value is 0, otherwise it produces a positive number. This can be easily seen from its plot. It's all above the horizontal axis and only touches the x-axis at x equals 0. Absolute value of x plus 5 is just a shift to the left by 5. So, it's always positive, unless when it touches x equal -5, which is 0. So, we put a -5 here, where the function is 0. Then if x is smaller than -5, the absolute value function is positive, and also is positive when x is larger than -5. We shall do the same for the other terms. Consider the second term in the numerator. It's a quadratic polynomial or quadratic function. We can analyze this term as a whole by finding its roots. But, it's easier to break it down by factoring. For this, first we factor a minus sign out so that the x squared term gets a positive coefficient. Now, in order to factor the quadratic function inside the parentheses, we find its root. That's easily doable by using the famous quadratic formula. In this case, b is -5, so we put 5 here, a is equal to 1, and c is equal to 4. So, b squared minus 4ac is 25 minus 16, which is equal to 9. Square root of 9 is 3. Thus, we get 5 plus -3, over 2. Taking the plus sign in the numerator yields 5 plus 3 equal to 8, so the first root is 8 divided by 2, which gives 4. And taking the minus sign in the numerator yields 5 minus 3 equal to 2, so the second root is 2 divided by 2, which is 1. Note that we could have found these roots easier without even using the quadratic formula. If you notice, the sum of the coefficients in the quadratic function is 1 minus 5 plus 4, that is 0. So, when this happens, one root is always 1, and the other root is c divided by a, which here is 4 divided by 1, that is 4. So, we get 2 factor of x minus 4 and x minus 1. Now, we can take the minus sign inside the first factor and write 4 minus x. We can now put these two terms in the table. Obviously, the term 4 minus x is 0 at 4, so we put a 0 here at x equal to 4. This term is negative when x is larger than 4, so we'll put minus sign here. And, it's positive when x is smaller than 4, so we put a plus sign for all intervals of x less than 4. Similarly, we put the term x minus 1 in the table. This term is 0 at x equal to 1, so we put 0 here at x equal to 1. It is positive when x is greater than 1. So we put plus sign for all those intervals. Also, x minus 1 is less than 0 when x is less than 1, so we put negative sign for all the intervals of x less than 1. The last item to investigate is the denominator. This term is a cubic polynomial, but it has a factor of x in each term that can be factored out. So, we have a product of x and a quadratic polynomial. First we put the term x in the table. Without any problem, we easily identifies its 0, and its sign. Now, we deal with the quadratic function as before. we should check if we can factor the quadratic function. If we use the quadratic formula, we see that the term inside the square root, which is b squared minus 4ac, is 1 minus 12 equal to minus 11, which is a negative number. So, there is no real root for the quadratic function here. That means the quadratic function is either positive for all ranges of x, or is negative for all ranges of x. Since the coefficient of x squared is 3, which is a positive number, we realize that the quadratic function is all positive. So, we put plus sign for the whole x range. Very good. We're almost done. We already determined the signs of all terms involved in the fraction for all ranges of x. Before we move on to determine the sign of the whole fraction in different intervals of x, let's a little arrange the sign determination table and put the signs in the aligned spots. Note that, since the sign change of each term may possibly occur at its zeroth, we could have first determined the zeroth of each term and arranged them on the x interval. This way, we would have had a nicer table, but doesn't matter, we do it now. Perfect. The sign determination table looks great now, and we're ready to determine the sign of the whole fraction. For this, we add another row at the bottom of the table, and write the whole fraction. Now, we use the product sign rule. Consider the product or division of several terms. If the number of negative terms is odd, then the result is negative, and if the number of negative terms is even, then the result is positive. So, for the x interval from minus infinity to minus 5, we have two minus signs, thus the result is positive. At x equal to minus 5, a term in the numerator of the fraction is 0, thus the whole fraction becomes 0. So, we put a 0 at x equal to minus 5, for the whole fraction here. From minus 5 to 0, we have again two minus signs, thus the result is positive. At x equal to 0, a term in the denominator of the fraction is 0, thus the whole fraction becomes undetermined or infinity. So, we put n at x equal to 0, for the whole fraction here, to represent a non-real value. From 0 to 1, we see only one minus sign in the corresponding column, so the result is negative. At x equal to 1, a term in the numerator of the fraction is 0, thus the whole fraction becomes 0. So, we put a 0 at x equal to 1, for the whole fraction here. From 1 to 4, we see that all terms are positive in the corresponding column, so the result is positive. At x equal to 4, again a term in the numerator of the fraction is 0, thus the whole fraction becomes 0. So, we put a 0 at x equal to 4, for the whole fraction here. And, finally, from 4 to infinity, we see only one minus sign in the corresponding column, so the result is negative. Now that we determine the sign of the fraction for the whole real valued x, we need to pick the acceptable intervals. The acceptable intervals are the ones in which the fraction is 0 or positive. So, from minus infinity up to minus 5 is acceptable, minus 5 is acceptable itself since the fraction is 0. We keep going with the acceptable interval since we still have a plus sign after minus 5. However, we must exclude the point, x equal to 0, because the function is undetermined there. From 0 up to 1 is still unacceptable since there is a negative sign, but x equal to 1 is acceptable since the fraction is 0, and 0 is acceptable. Likewise, from 1 to 4 is acceptable because of the plus sign. X equal to 4 is acceptable too, since the fraction becomes 0. Finally, for x greater than 4, the fraction is negative, so the interval is not acceptable. Great. We solved the problem. It's better though to write the solution in terms of the set of intervals of the real number. So, the solution is the following set of x such that x belongs to the open interval from minus infinity to 0, union with the closed interval of 1 to 4. Note that where we used an open set symbol or a closed set symbol, I emphasize here that, for minus or plus infinity, we always use the open set symbol since these two infinities are not included in the set of real numbers. We used an open set symbol for 0 since 0 is not in the solution. We used closed set symbols for 1 and 4 since both of them are included in the solution. That concludes the solution. By the way, if you're interested in learning more about the basics of set theory, it is discussed in Lecture 2 of the Non-Specialist Calculus course, and if you're interested in learning more about inequality solving, it is discussed in Lecture 3 of the Non-Specialist Calculus course. Links in the description below. Hope you enjoyed it. If you did, please make sure to like and subscribe. Keep in mind that the aim of this channel is to represent the beauty of mathematics and physics, and the pure connection between them. So, watch other videos on our channel, and support us with your comments and suggestions. See you next time.